y is a function of x of some sort. This would be an example of a differential equation. Yes?
Is that y prime or is that y1?
Y prime. They come in all sorts of forms. Y delta y minus 7y prime plus 10y equals 0. These are all forms of potentials, yes?
The first, where you said let y equal y of x, what does that have to do with these three?
All of the y's that you see are functions of x.
Okay.
Sometimes they're functions of t, time. By the way, okay, so these are what's called ordinary differential equations, meaning y is only a function of one domain variable. Later, of course, you'll have multivariable, and so the real differential equations end up being what are called partial differential equations. You won't learn what a partial derivative is until next semester, and then you got to work backwards. I know. So here are some examples. Let's talk about ways to solve these.
So he means multiple variables for the value of y for one domain.
We're going to talk about population
What?
growth.
Smart.
Let me find a good chart, actually.
I can't see the top.
So here's what population growth is.
That
Quick check this.
open.
Population growth is, it ends up being an exponential function, but I kind of want to talk about it a little bit differently. When we're talking about population growth, I'm not talking about people population growth. People population growth is way too erratic. There's too many things going on. There's wars, there's famine, there's disease, there's good times, there's bad times, there's political times. So it's really hard to put a model for population growth. The type of population growth we're talking about are going to be things like bacterial growth in a controlled environment. A constant temperature, a constant pressure, almost unexhaustible food source, and things like that. That way we can control the population as we do this. What I want to do is talk about we're going to have P, which is a function of time. It's going to be the actual population at time t, I should say. This might be a new symbol for you. This is the letter P. This is directly proportional to P. Meaning, the faster the change in population, the larger the population. There's a connection between the two. We would use, yes?
I'm sorry, what was that symbol called again?
Directly proportional to. Or direct variation, sometimes it's mentioned. I want to view it like this. It's like an infinity symbol without the missing side. It's kind of like this. If I have two sets of numbers that are very closely related, as one gets larger, the other gets larger. For example, let's say I want to put the number of gallons of gas in my car. So I go to my dumb little Prius and I put in 5 gallons in my car. Do I pay $5? No, but as soon as I know how much each gallon is, I can immediately, so let's say it's $4 a gallon. So as soon as I choose to put 5 gallons into there, how much money is it going to cost me? Now, if I put more gallons of gas, you see it's going to cost me more money? The numbers aren't the same, but they're connected. That's what we're doing here. If the population explodes, if it grows very, very quickly, then the population itself is also going to get very, very large. The rate at which it grows is not going to equal the actual population itself. Make sense? Now there's a way to make these two things equal, just like with the gasoline, is we need to know the price of the gasoline, or we need to know a constant of some sort. Proportionality. That balances them out. Again, that's like the price of gas. Here we have a differential equation. I have the derivative of a function and the function embedded in the same piece here. We're going to do something that's going to seem a little weird. We're going to actually solve this differential equation using a method called the separation of variables. Please keep in mind, p is a function of t, time. I'm going to multiply both sides by dt. Technically, that's not what I'm doing, but that's what we're going to do. I'm also going to move the p to this side. It's just algebra. Oh, I've invited some of my other classes to come Sunday. So there may be times when there's a lull or something, I may have one or two of you go in there and try to help them out a little bit if they're getting stuck on a few things. Not that you guys need to brushing up on your algebra. What's that? Oh, yes, I'm missing. Yeah, for sure. Thank you. Okay, better? Thank you. You're welcome. Now we're here. Integration is what we call a linear operator. We're going to go and apply integration to both sides of this.
You don't want to be left-hander. I love it. It's so hard.
What happened to the plus c over here? I just moved it to the other side. Yeah. We're going to abuse this notation quite a bit, actually. K is a constant, C is a constant. Next semester, you're going to love this. Your constant of integration is going to be a constant relative to what you just integrated against. So it's possible that C will be a function of y and z. I know. Pretty cool. Please note, the population cannot be negative. What does that even mean, right? If I think of bacteria and they're all dead, I'm not going to have a negative 1 bacteria, right? So I don't need the absolute value anymore. I'm going to change this into exponential form. Please please don't make it e to the kt plus e to the c. It's the whole side becomes the exponent, just like we've been doing here. There's an exponent. I just want to see your reaction. Let's see what you do. Make sure your neighbor understands what just happened there.
Do you know what just happened there?
That doesn't seem right.
Remember this?
Oh.
You do remember this, right? Remember pre-algebra when you learned this? 7th grade? Alright. I actually used this rule backwards. It's easy to forget, I get it. So I actually used this rule backwards. Now e to the c is just another constant, right? So I'm going to rewrite this like this. So let's say I get a petri dish. This is obviously large for a petri dish, but you get the idea. We have a petri dish here, and I put an initial population on there. In other words, I put just a few samples of bacteria cells in here on some sort of agar-rich whatever, and we put it in a nice heated area and make sure the temperature is the same and everything like that. Whatever that initial amount that I put on there is, that's going to be our initial amount. That's not going to change. That's going to be wherever we start. So as we do this, I'm going to say at t equals 0, p of 0 is going to equal c e raised to the k times 0 power. At time 0, we are agreeing that that is our initial population. What's e to the 0 power again? 1. So our constant, our capital C, our new C, this one here, is actually the initial population. This will be important to us in the later section. K is the percent growth. So if you say the population growth is at 3%, it'd be 0.03. K would be. Yeah, we're not going to prove that right now, but it is. You trust me, right? So if I knew what K was, and I knew the initial population, if I said, hey, after 2 days, what's the new population? Well, I just pop it into here, line it up, and then for the new population. And it'd be pretty accurate, especially if it's in a very controlled environment. Questions? This is sort of our first mess with differential equations. Usually I don't start with a practical example, but I thought I'd try something different this time. Yeah?
K be negative.
Yes? K can be negative. In fact, we use this exact same formula for radioactivity, radioactive decay. Yes?
Yes, I missed your explanation on how the plus C went out on the left side. The integral.
I just moved it to the other side.
Oh, okay. So I was under the impression there were supposed to be 2 plus C's, one on this side, one on this side.
Yeah.
That's why I'm confused. Okay. All right.
No more Yeah.
Alright.
So again, when we can abuse that plus c, we just kind of dump everything into that when it's a constant.
Okay.
Anyone else? Alright, we're going to start at the beginning now. I'm going to give you a differential equation and a possible answer. I want you to think back to your beginning algebra days, way back in the day. When you first